Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is 2.4, which is continuity and one-sided limits. All right, so first let's look at what the definition of continuity is. All right, so here we go. So we have two kinds of continuities. We have continuity at a point, and then we also have it on an open interval. But first, let's discuss the continuity at a point. A function is continuous at C when the three following conditions are met. When all three following conditions are met. And here they are. The first condition is that f of C is defined. All right, so what we're saying there is that the function must have an actual value at that point. All right, it cannot be an open hole, it cannot be an asymptote, it must be an actual point. All right, so the first thing is that f of C is defined. That is the first condition. The next condition is that the limit as x goes to C of f of x exists. All right, and the third condition is that, well, that limit as x goes to C of f of x is actually equal to f of C, the value at C. All right, so that is continuity at a point. Now, let's look at the definition of continuity on an open interval. All right, so a function is continuous on an open interval on an open interval AB, right? I notice it's open interval because it's parentheses. When the function, when it is continuous at each point in that interval AB. All right. So essentially, it's saying that throughout that entire interval, those three conditions are met at every single point. All right. That's what continuity on an open interval is. Now, let's look at three visuals, or a few visuals actually, as to how continuity may fail to exist. So here we go. So let's say that this is our open interval. We're starting at A, we're going to B, right? And it's an open interval, so perhaps I'll put parentheses here to signify the open interval. So a function like this would fail to be continuous, all right? And it would be because of that hole in the middle. So maybe draw that. There we go. So that would fail to be continuous because of this hole. So this fails essentially the first condition. So in here, f of C is undefined. Well, this value here being C. All right. So the next way that it can fail to be continuous, it would be, so let's look at this. So here's A, here's B, and let's say that we have something that looks like this. All right. So in here, this is not continuous because, well, it fails the second condition. The limit doesn't exist at c, right? So in here, the limit as x approaches c of f of x does not exist. So that's why this fails to be continuous. And the third way that this can fail to be continuous, so let's say here's A, here's B, is if we had something like this, right? It'll look very similar to the first scenario, except now we've got this point down here, all right? So in here, the what this fails is um, the third condition, right? The limit does not equal the value. So in here, the limit as x goes to c of f of x does not equal f of c. So that's why that fails to be continuous. All right. Now, let's look at what something that is continuous on an open interval looks like. So, well, perhaps I'll say these three are not continuous. Not continuous. And this one fails, so I'll put it in bracket, fails condition 1. This one fails condition 2. And this last one fails condition 3. All right, so all of these are not continuous. And let's look at what is continuous. So here's A, here's B. So something like this, well, let's draw that better. Something like this, that is continuous. Let's say here's C. Right here at C, it is defined, and the limit is does exist, right? That ends up being continuous. So in layman's terms, essentially continuous means that you could start at one point and get to the other without having to lift your pen or pencil from the paper. All right. Um, so that's continuity in layman's terms. But in terms of calculus, because this is a calculus course, this is what we want to make sure we say about continuity. All right. Now, a quick note here, and this is just nomenclature. So note: if f is not continuous at c, we say f has a discontinuity at c. All right. So, or we can say it is discontinuous at c, or it is discontinuous at c. But we normally say it has a discontinuity. All right. Um, so that's just saying again that it fails to be continuous. Now, there are two types of discontinuities. All right. So types of discontinuities. All right, and this is what they are called. They're called removable and non-removable. So let's talk about what a removable discontinuity is first. So this happens when the limit as x approaches c of f of x exists, but the limit as x approaches c of f of x is not f of c. Right? So when the limit exists, but it is not um, the actual value at that point. So in terms of, well, first I'll give you the definition of non-removable, and then we'll look at what each of them might look like. So that's removable. So non-removable. Now this happens when the limit as x approaches c of f of x does not exist. All right, and I'll put in parentheses here, even if f of c is defined. All right, so that would be a non-removable discontinuity. Now, graphically speaking, so let's look at these three up here. All right, um, this first one is a removable discontinuity. The limit exists, right? The limit exists, and that's all we needed to make sure to for it to be a removable discontinuity. The limit exists, and in here, even though the function's not defined at c, well, the point is that it is not, um, that the limit does exist. Similarly, over here in this scenario over here, the third one, in there, this is also a removable discontinuity because, well, the limit exists even if the value of the function is not that limit. So both scenario 1 and scenario 3 would be removable discontinuities. This one in the middle is one possible way that we can get a non-removable discontinuity because the limit doesn't exist. All right. So if the limit doesn't exist, it is a non-removable discontinuity. Um, Another way that it could be a a non-removable discontinuity is if you are approaching an asymptote, a vertical asymptote. All right. So now classify the discontinuity. And here we go. So here I have f of x is equal to 1 over x. All right. So first, let's recall that the domain here is that x cannot be equal to 0. So we're going to classify that discontinuity at 0. All right. Now let's look at the graph. The graph here of 1 over x looks as follows. All right. So that is essentially the graph of 1 over x. Now in there, notice that we've got a vertical asymptote going through x equals 0. This is our vertical asymptote at x equals 0. So the real question that we're asking here is, well, does the limit as x go to 0 of f of x exist? And the answer to that is no. All right, so because it does not exist, well, right away, this implies that we're dealing with a non-removable discontinuity. Non-removable spelling. All right, non-removable. All right, so that's A. B. Let's say that I have g of x is equal to x squared minus 1 over x minus 1. All right. Notice that the domain here is that x cannot be equal to 1. That's the domain. So we're going to be figuring out what's going on around that discontinuity, whether it is removable or not. All right. So in here, um, let's let me show you what this actually looks like. Um, so x squared minus 1 looks like this. But here we are not defined, right? So there's no value there. And that would be at the height of 1. All right. So that's what that graph looks like. All right. So again, the real question here that we need to ask ourselves is, does the limit as x approach 1 of our function exist? And the answer is it does, right? Graphically speaking, we can right away say that it does. Yes. So because it does exist, this tells us that this is a removable discontinuity, right? Um, all right. Before I continue, um, I wanna I do want to mention something about a visual for these removable discontinuities. Essentially, what we're saying here is if I can take a pen and just fill in the hole by making one dot in there, right? So by just putting in 1 point, if that makes it continuous, then it is removable, all right? Because we can get rid of that discontinuity by just filling it in with 1 point, all right? All right, so that's B. C. Let's say that we had the following function. F of x is equal to um, this piecewise function. X plus 1, where x is less than 0, and e to the x minus 1, where x is greater than 0. All right? So notice here that my domain is x cannot be equal to 0. So we got to figure out what's going on there, right? We got to figure out what's going on around 0. So in here, let me give you the visual. This function looks as follows. Let's put that lower. So it is x plus 1, right, for values that are less than 0, and e to the x minus 1 for values that are greater than 0. And e to the x minus 1 looks like this, right? Let's draw that better. There we go. It is an exponential function there, all right? Now, in here does the limit exist? So the limit as x approaches 0 of our function, does it exist? All right? That's the question that we're asking here. And the answer is no. All right? The limit does not exist. Because, well, even if, I mean, we see from the left it's going all the way up to this value, and from the right it's going all the way down to this value, right? So in there, we can right away say that the limit doesn't exist. Now, going back to the idea of just being able to fill this in and making it continuous, right? Um, and the idea was that we only needed to draw 1 point. So if I draw this point, that still doesn't make it continuous. If I draw this point, that still doesn't make it continuous. So this is clearly a non-removable discontinuity. But we already knew that because the limit did not exist. So this is non-removable. All right. Now D. Let's say that I have f of x is equal to x minus pi times sine of x over x minus pi, right? And in here, notice that the domain is that x cannot equal pi. All right, now in here, this is what we get for the visual. So this is sine, all right? In general, this is what sine looks like. All right, and except this one, because x cannot be equal to pi, that region right there would be a hole. So let's make it look like a hole. There we go. That was too much. Oh, way too much. All right, good enough. It keeps drawing over the things I don't want to. All right, now that visually we can see that we can just put in a point there, right? We can just put in a point there, right there, and now it's continuous, right? So visually right away we know that this is removable, right? So here, but really what we need to do here is figure out, whoa, let's not write that. The limit as x approaches pi of our function. Does it exist? And the answer is yes. All right. From both sides, it's approaching 0. So in here, this tells us that it is removable. All right. Now, that was um, classifying them visually. All right. But let's talk about how do we know um, with calculus whether or not the limit exists. So here's the thing, and this again is we need to figure out if the limit exists. All right, but for a lot of cases, all right, this one I can rewrite it, right? This can be rewritten as x plus 1 times x minus 1 over x minus 1. And this happens in a lot of cases where x minus 1 gets canceled out, right? And and we end up with just x plus 1 as long as x doesn't equal to 1, and that's from the domain, right? So in there, notice that we canceled out that x minus 1. Essentially, we removed the x minus 1, all right? So in there, that's how we know that that is a removable discontinuity. Um, Similarly over here, if I was trying to figure out the limit of this, wait, hold on, that was B, yeah. In A, there's nothing that I can do to rewrite this to get rid of that x, right? There's nothing that I can algebraically do there. That's also true for C. There's nothing that I can algebraically do there to get rid of that 0. But D, in D, we can cancel out this x minus pi, and we end up with just sine of x as long as x doesn't equal pi. And again, we canceled out that x minus pi. So essentially, we removed it from our function there, all right? So essentially, if you can cancel it out, it is likely a removable discontinuity, all right? And if you cannot cancel it out, it is likely a non-removable discontinuity. All right, so now let's talk about something called one-sided limits. We already spoke about limits, but these are one-sided limits. So, one-sided limits. And we have limits from the right. So from the right and from the left. All right. And essentially here what we're doing is we're just introducing notation. So this is the notation for a limit from the right. We will write it as limit as x approaches c from the right of the function. And we would say that's equal to L. Similarly, we would say the limit as x approaches c from the left of f of x is equal to L. So essentially what I'm doing there is I'm writing that plus to signify right, and that's going to be kind of like a little exponent to that c. And similarly, to signify that it's from the left, I'm going to put a minus sign as an exponent to that c. All right, so that tells us that it is from the right and from the left. All right, so again, that's just notation. Now, why do we care about limits from one side or the other? Well, let's consider the following equation, for the following function, sorry. So let's say that f of x is, so consider this function. Consider that f of x is something like the square root of 9 minus x squared. All right. Now in here, all right, this specific function, this is what it looks like. All right. So it is a semicircle of radius 3, and it is the positive part of it. So let's say that this is 3 and that's negative 3, close enough. And this is what the function looks like. It is a semicircle. Yeah, let's try it. Let's see if I can draw that better. I guess it's a little bit better. At this height being 3. All right. So that's what that function looks like. Now, if we were to ask the question, um, what is the limit as x approaches 3 of f of x, right? What is the limit as x approaches 3? Now, the problem with that question is that for the limit to exist, it must be the same thing going from both sides, right? But this, yeah, it can come from the left, but there's nothing over here on the right. So we can't, there's no way that we can say that this is actually doing the same, that they're both going to the same value from either side. All right, so that's what we would want to care about, these kinds of one-sided limits. So in here, we would say this is undefined. All right, the limit is undefined or does not exist, um, because, well, there's nothing on the right side of 3. But if I were to say, what is the limit as x approaches 3 from the left of our function? Well, then now we can confidently say it's 0, right? So we're approaching 3 from the left. The function is going to the value of 0. All right. Um, so that's one of the reasons we care about one-sided limits. We can also consider, a step function. So something like g of x is equal to this. If you don't recall what this is, you might have seen it this way. This is called the greatest integer function. Greatest integer function. And this greatest integer function is also sometimes called the floor function. And this floor function, visually is the step function. So this is what it looks like. Um, so it looks like this. Well, perhaps I'll do this in a different color. There it is. All right. So in here, and I mean this repeats forever and ever in both directions. Right? So that is the floor function. So for example, here I can ask the question, well, what is the limit as, um, well, as x approaches 0 of the function? And well, here's 0. It's not doing the same thing from either side, so that does not exist. We can say, well, what is f of 0 then? Well, f of 0 is 0. It's defined to be 0, right? That's where it's filled in. All right. Well, if it's defined there and the limit doesn't exist, well, what's happening from either side? Well, we can say the limit as x approaches c from the right of the function, c from the right of the function, it is, well, 0. But if I take the limit as x approaches c from the left of the function, so we're approaching 0 this way from the left, well, we're at -1. All right. So in there, the limit from either side was different, which makes sense because we already said the limit does not exist. All right. Um, so this is another kind of function where we care about one-sided limits. All right. Notice now that we can say that this is not continuous at 0, right? Because even though it is defined there, the limit doesn't exist. So it would not be continuous at 0. So that's a little, yeah. So in here when we have these kinds of discontinuities, we want to be able to take, one-sided limits to see what's going on around those discontinuities. All right. Now let's, talk about something called the existence of a limit. So theorem. The existence of a limit. All right. So if I let f be a function, so let f be a function, and let L be a real number. All right. If the limit as x approaches c from the right of the function equals L, and the limit as x approaches c from the left of the function also equals L, then the limit as x approaches c overall of the function is equal to L. All right. So, I mean, we had already spoken about that as an idea. Essentially, this is saying if the limit from the right and the limit from the left is both the same value, well, then the limit is that value. All right. We had already spoken about that as an idea overall, but now we're just writing it in terms of calculus. Now, definition of continuity on a closed interval. So this is definition. Continuity on a closed interval. Let's say, so a function f is continuous on the closed interval AB if f is continuous on the open interval AB and the limit as x approaches a from the right of f of x equals f of a. Let's rewrite that f of a better. F of a, and the limit as x approaches um, b from the left of f of x is equal to f of b. We say, so if that's true, we say that f of x is continuous on from the right, excuse me, from the right at a and from the left at b. All right. Now what? So in here, what we're actually doing is we're extending the definition of continuity to include to include closed intervals. All right. If you recall, when I said where is it? Where I defined continuity, um, I did it on an open interval. Right here it is. So it was only on the open interval from A to B, not including the endpoints. But now with this new definition, we can actually include the endpoints to talk about something being continuous. All right, but we would say that it's continuous from the left or from the right. We wouldn't say that it's just continuous. All right. So let's look at a function that behaves in such a way. So if I have f of x is equal to the square root of 2 minus x, right? In here, let's recall what the domain is. The domain here would be where 2 minus x is greater than or equal to 0, so therefore x is less than or equal to 2, right? That is our domain. So what we really want to do here is what we want to figure out is what's going on around 2, right? And notice that the domain is less than or equal to 2. So what we're really trying to figure out is what's going on from the left of 2. So if we go ahead and take this limit, what we're going to say is, well, let's figure out the limit as x approaches 2 from the left of our function. Well, that would be the limit as x approaches 2 from the left of the square root of 2 minus x. There's no issue with plugging in 2, so I end up with just 0, right? And now, what is f of 2? Well, f of 2 here, well, that would be 0, right? 2 minus 2 is 0. So both of these together tells me that f of x is continuous from the right, not from the right, from the left. We were at the left. From the left um, of x equals 2. And that's just left, right? Left. Way better. All right, cool. So that's what we care about the one-sided limits here and continuity. Graphically speaking, it would look something like this. Here's 2, and then is that. So in here, we're able to say now that this is continuous on its entire domain. Right? This is continuous from the left of 2 and for all the values to the left of that. So now, let's do some properties of continuity. All right. Properties of continuity. Let B um, be a real number and let f and g be continuous functions at c. Well, I'll write that at x equals c. All right. Then the following are true. All right. The following are also continuous at c. All right. So this is essentially properties of continuity, how they deal with combinations of functions. All right. Let me rephrase that. Um, I don't want to say combinations. Instead of saying that, well, arithmetic combinations. There we go. Arithmetic combination sounds better. So in here, let's say that if I had b times f, if f was continuous at c, then b times f is also continuous at c. All right. Um, if I have the sum or difference of the two functions, well, if f and g were originally continuous at c, then the sum or the difference would also be continuous at c. If I have the product of them, f times g, right? And again, if f was continuous at c and if g was continuous at c, then the product is also continuous at c. And lastly here, let's say that we had f over g, right? In here, we had to make sure that g of c does not equal 0. But as long as g of c is not equal to 0 and g is continuous at c and f is continuous at c, then their quotient would also be continuous at c. So essentially, what this is telling us is that all of the following would be continuous on their domain. So the following, well, I'm not going to write that sentence. So the following are continuous on the domain. So continuous examples. So if I have something like f of x is equal to x plus e to the x is continuous, e to the x is continuous, so their sum is continuous. If I had something like 7 sine of x minus 4x squared, all right, and there sine of x is continuous, so 7 sine of x is continuous, x squared is continuous, so 4x squared is continuous, and their difference would also be continuous. If I had something like f of x is equal to x squared minus 1 over, let's do x sine x. No, just do sine x, right? This would be continuous um, where sine of x does not equal 0. But otherwise it would be continuous, all right? So that's what this allows us to do. We know that some of these functions are continuous on their own, So we're able to tell by arithmetic combinations whether or not they're also continuous. Now, this is not the only way that we can combine functions. We can also do composition of functions. So, theorem, and this is continuity or continuity of composite functions. Now, composite functions are always a little bit trickier as far as how we state it. So, in this case, it's not that bad. If G is continuous at C and F is continuous at G of C. Remember, G of C is just some specific number now, right? C is a number, G is a function, G of C is the value that you get when you plug in C. So if F is continuous at whatever that value is, then F composed with G of X is continuous at C. All right. So that allows us to see that. All right. So now let's answer some questions here. On what interval are or intervals, I should say, interval or intervals are the following continuous? All right. So let's say that we have f of x is equal to tan of x, right? And in here, what we're gonna say is, well, this function, let's look at what it looks like. So in here, this is what it looks like, right? Well, on what intervals is this continuous? Well, pretty much wherever it doesn't have this asymptote. All right. So in here, in general, the domain for tangent is x is equal to pi over 2 plus or minus n pi because the period of tangent is pi. So that would tell us, well, that this is continuous. So it has to be continuous on its domain, and the domain is x cannot be equal to those values. All right. So that would tell us now that this is continuous on, well, negative 3 pi over 2, negative pi over 2, comma, from negative pi over 2 to negative 3 pi over 2. What? No, to positive pi over 2. I messed that up. To positive pi over 2. Then from positive pi over 2 to 3 pi over 2. And so on and so forth in both directions. All right. So it's continuous on its domain. All right. Now, so in there again, all we're doing is, well, we're just looking at the function and saying, well, where would that be continuous? Well, wherever we don't have those asymptotes. Um, F. Let's say that we have g of x is equal to this piecewise function, sine of 1 over x, where x is not equal to 0, and 0, where x equals to 0. So in here, let me give you the visual. So this is the visual. And you may or may not recall this, that it is in another video, this function of sine of x, sine of 1 over x. But it looks something like this. And it starts oscillating faster and faster and faster and well, and then it slows down, and it looks something like that. All right. And in here, we're also saying that the value at 0 is 0. So we've got also that point. That's not that visible. Let's use a different color. Let's do red. Way more visible. So that is this point. That's not red, that's pink. Whatever, it works. Now, in there, the question here is this continuous? Is this continuous? Well, let's figure this out. The value at that point, so f of 0 is 0. What we need to figure out is, does the limit as x approaches c, or excuse me, in this case 0, of our function, is that going to be equal to 0? Right, because we want it to be f of 0. So maybe I'll write it as f of 0. And well, this is saying the limit as x approaches 0 of sine of 1 over x. Now, you may or may not recall this when I was talking about when I first introduced this function. But the limit of this does not exist. So because it doesn't exist, it fails to be continuous at 0. All right, so this is not continuous at x equals 0. Not continuous at x equals 0. So that tells us now that this is continuous on negative infinity to 0 and 0 to infinity. All right. Now, let's talk about something called the intermediate value theorem. Right? So, the intermediate value theorem. We abbreviate it with IVT. All right. Now, if f is continuous on the closed interval AB, and f of a is not equal to f of b, and k is some height between f of a and f of b, not including f of a or f of b, then there exists at least one c in the interval, in the open interval AB, such that f of c equals k. All right, so I'll read it again. It says, if f is continuous on the closed interval AB, where f of a does not equal to f of b, and k is some value, some number between f of a and f of b, then there exists at least one value c in the open interval AB, such that f of c equals k. All right, so let's get the visual to what this is saying. All right, so here we go. So let's say that here's A and here's B. And let's say that here is the height f of A and up here is the height f of B. So here's f of A and here is f of B. All right. So let's do this. In here, we're gonna say that, well, we have some height k, in between f of a and f of b. Now, if the function that I draw here is to be continuous, so something like this, that's a continuous function, right? If that is actually continuous, then that means that there's at least one value where k is the height of the function. So there's at least one c. So that's c sub 1, here's c sub 2, here's c sub 3. In this case, I drew 3 of them, but it doesn't have to be 3. What this tells us is it guarantees at least 1, right? So a simpler version of this would be perhaps, and I'll do it in a different color, a function like this. right? And there it was only hit by the height k one time, right? You know what? Maybe I'll just redraw it. And by redraw I mean copy and paste, and just get rid of that function. Because I want you to see the two possibilities there. So let's say that in this case we had something like that. All right. So in there, whoa, I forgot to. All right, there it is. So in there we're saying that because the function is continuous, it needs to be hit by that height at least once. So in this case, we don't have this many c's, we only have one of them. All right. So there you go. Um, all right. So again, the intermediate value theorem is telling us that we must hit that height at least once. Another way to think about that is, well, let's think about it this way. At some point, right? At some point in your life, you were probably about 2 feet tall. All right. At some point in your life, you were about 2 feet tall. But now you're not 2 feet tall. You might be 5'5", you might be 5'10", whatever it is. The point is that you did not go from being 2 feet tall to being 5'5" without hitting every single height in the middle, right? Because your growth is a continuous function, right? It wouldn't make sense to say that, well, one day you were 5'1", and then the next day you were 5'7", right? That's not possible. That's not possible for you to have skipped all those heights in between, right, from one moment to the next. Um, it might be that it is possible to have fast growth, right? But I mean, that's more for biology class. The point here is that you you would not be able to go from one height to a different height, to a higher height, um, assuming normal circumstances, without getting without hitting every single height in between. All right. So that's what this is saying. So for example, well, before that, so this in these two scenarios, notice that f of x is continuous, right, on that interval a b. Um, we also have that f of a is not equal to f of b, and we also have that um, it actually did pass it. So in here, this is so by intermediate value theorem. Um, well, this is what the intermediate value theorem is, right? So the intermediate value theorem is guaranteeing that k is actually being hit at least once. Now, it is important for this to be a continuous function for the intermediate value theorem to apply. How come? Well, let's see. If I have a and here's b, let's say that I had this function. Um, well, let's do it this way. And something like that. All right. And this right here was the value of k. Well, notice that the fact that this is not continuous, I mean, even though the f of b and excuse me, f of a and f of b, um, even though they are at different heights, so f of a does not equal f of b. This value here in the middle is not at all guaranteed, right? It is not at all guaranteed. This height of k is not guaranteed by the intermediate value theorem here. So in here, no c exists. No c exists such that no c exists so that um, k or f of c equals k, right? Now, let's see how to do a problem or two with the intermediate value theorem. All right, so let's say here that let f of x be equal to x cubed minus x squared plus x minus 2 on the interval 0, 3. All right, and let f of c be equal to 4. Is c guaranteed? So we guarantee to have a value of c in this interval so that when I plug in that c, I get a value of 4. Is that guaranteed? Well, let's find out. First, we need to figure out what's going on at each edge of the interval. We need to make sure they are at different heights. So f of 0 will be equal to -2. All right. Next, f of 3 would be equal to, well, 3 cubed, that's 27, minus 3 squared, that's 9, plus 3 minus 2, which gives us 19, right? 27 minus 9 is 18, 18 plus 3 is 21, 21 minus 2 is 19. So in here, this tells us now that f of 0 does not equal to f of 3. Good. We are at different heights at each end of the interval. All right. Now, so the next thing we need to check is, well, is the value 4 in between those values? So is 4 between -2 and 19? Yes, it is. All right, so 4 is in the interval. Using the previous notation that I had, I could say 4 is in the interval from -2 to 19. So in here, now we can say by intermediate value theorem, um, AC exists such that, or so that, f of c is equal to 4 um, on the interval, somewhere on the interval. Let's just write int on the interval. There we go. All right. So that's one possible way to use it here. All right. Now let's look at another way to use the intermediate value theorem. So this is example H. Now let g of x be equal to x squared minus 6x plus 8 on the interval 1 to 3. All right. Where, and the question here, what we're saying here, f of c is 0. All right. Is c guaranteed? Notice here that since I'm saying f of c is 0, what I'm really asking here is, does this have any x-intercepts, right? Because x-intercepts are when y is equal to 0. So this question is essentially saying, are there any x-intercepts in that interval? Are there x-intercepts in the interval from 1 to 3? All right. And we're not looking for what they are. The question is just, are there any? Not what are they? Are there any? All right. So in here we're gonna say, well, let's figure out what happens when we plug in 1. So I have g of 1 is equal to, well, 1 squared is 1 minus 6 times 1, which is 6, and then that plus 8. 1 minus 6 is -5, plus 8 is 3. Now if I plug in 3, 3 squared is 9, 6 times 3 is 18, 9 minus 18 is -9, -9 plus 8 is -1. All right, so in here, was g of 1 not equal to g of 3? Yes. All right, so that part's satisfied. The next question is 0 in between -1 and 3? And the answer is yes, it is. Right? So now this tells us that by intermediate value theorem, a C exists such that, or so that, f of c is 0. In other words, it does have an x-intercept somewhere in that interval. All right. Um, cool. So now, the next thing that I do want to say here is why is it important, and perhaps I should have said this earlier, why is it important that f of a does not equal f of b? All right. The reason that's important is, well, let's say that here's a and here's b, and here's f of a, which is f of b. If they're at the same height, well, you can't guarantee that this is not what the function looks like, so it doesn't even make sense to talk about a k value in between those two. All right, so that's why we don't consider that scenarios where f of a equals f of b. All right, it is not guaranteed that you're going to be hitting any other value of any other y value besides those. So that's why we care that those two are not the same. All right, I'm gonna get, well, I'll leave it. All right. All right. So the next thing we're going to do here is I want to do a couple of examples on classifying discontinuities. All right. We did them, I mean, I did them earlier on just the visual end of things, but I want to do them with actual calculus more. So let's look at some examples. So in here the question is classify the discontinuities. So find the domain and classify the discontinuities of f of x. The discontinuities of the given function. All right. So let's say that I had, for example, something like, and we start simple. Let's say that I had f of x is equal to 4 over x minus 6. All right. If you recall, from what I said earlier was that to figure out, well, we had two types of discontinuities, right? Removable and non-removable. So to classify them, what we need to see is, well, are they going to be, well, that's what they're asking for us. Like, are they going to be removable or non-removable? So first, let's look at the domain. Here, the domain is x cannot be equal to 6. Now, whether or not the function, excuse me, the discontinuity is removable, came down essentially to just one question. Does the limit as x approaches c of our function exist? So we had 4 over x minus 6, and our c was 6. And in here, the answer is it does not, right? Because when I plug in 6 into here, I get 4 over 0, which is undefined, so it doesn't exist, right? And there's nothing algebraically that I can do to rewrite this, right, to get rid of that. But for example, if I had something like f of x is equal to x over x squared minus x, all right? So in here, let's first find the domain. So in here, the domain is that x squared minus x cannot be equal to 0. So x times x minus 1 cannot be equal to 0. All right, so that means that x cannot be equal to 0 and x minus 1, excuse me, and x cannot be equal to 1. All right, so we need to figure out what's happening around those. So the question here is, well, does the limit as x approach 0 exist? All right, so in here we have x over x squared minus x. Well, in here I can rewrite this really as the limit as x approaches 0 of of x over x times x minus 1. And at that point we see that the x's cancel out, so I end up with the limit as x approaches 0 of 1 over x minus 1. And now if I plug in 0, there's no issue. 0 minus 1 is -1, so I get -1. So that tells us that x equals 0 is a removable discontinuity. And as I mentioned before, notice that essentially I canceled it out, right? I removed it from our limit. If I said, well, let's look at the limit as x approaches 1 of x over x squared minus x. I mean, we already know what this simplifies to. We have the limit as x approaches 1 of 1 over x minus 1. But now, I mean, if I still can't plug in 1, right? Even though I simplify this, I still can't plug in 1. So this is undefined, which tells us that tells us that x equals 1 is a non-removable discontinuity, all right? So if the limit exists, it's removable. If the limit does not exist, it's non-removable. All right. Now let's look at a different kind of problem with these. All right. So in here, we are going to have discontinuities on these. All right. And these are all going to be removable discontinuities. But we're going to do here, so the instructions are find a constant a, find the constant a such that the function is continuous on its entire domain. All right, so essentially here, what this is saying is we are going to have functions that have removable discontinuities, but we want to figure out what the value of a should be. So let's do an example here. So what am I at? C, right? And I don't think this are accurate in comparison to what I started with. But anyway, um, so let's say, for example, that I had f of x be this piecewise function. All right, we're going to have 3x squared for values of x being greater than or equal to 1, and ax minus 4 for values of x being less than 1. And in here, what we want to make sure that we get is the value of a, right? That's what the question was about. Find the constant a so that this is overall continuous. Well, remember that for something to be continuous, and perhaps I'll write it in yellow on the side over here, to be continuous meant that we had to pass three conditions. F of um, f of c is defined. The limit as x approaches c of f of x exists, um, and that limit is f of c, right? So those were the three conditions that it had to pass. So in here, well, also recall that for the limit to exist, it must exist from both sides. It must be the same value from both sides, right? So from here for 2, we know that um, if the limit from the right equals L and the limit from the left equals L, then the limit overall equals L. So I'm going to be using all of these ideas in order to figure out what the value of A should be. So essentially, well, let's figure out what's going on here. So here this tells us that we're working around 1. So the first thing I want to figure out is what is f of 1? Well, f of 1 would be 3 times 1 squared, which is just 3. Cool. So it is defined. Good. That's what we defined it to be, right? I can't plug in 1 to the bottom. But I need the limit to exist. And for the limit to exist, I need the limit from both sides to be the same. So if I take the limit as x approaches 1 from the right of f of x. Well, we're approaching it from the right, so that means we're at higher values of 1. So that means we're in this part up here. So we're going to say that this is the limit as x approaches 1 from the right of 3x squared, which is just 3. All right. Now, the next thing, the limit from the left. The limit from the left of 1 of our function. So now we're on the left of 1. So this is what we're using down here. And this is going to be the limit as x approaches 1 from the left of ax minus 4. If I plug in that 1 in there, I end up with just a minus 4, right? But now that a minus 4, I want it to be the same exact thing as the limit on the other side, so I want this to be actually equal to 3. So we want, and this is want, right? Maybe I'll rewrite it. Want, we want a minus 4 to be equal to 3. So that tells us that a has to be equal to 7. And there we go. Now, with that value of a in there, now it is continuous. All right. How come? Well, we've got the limit from the right and the left, right? So this is how we would verify the limit from the left. So the limit as x approaches 1 from the left of 7x minus 4. Well, plug in 1. 7 times 1 is 7 minus 4 is 3. And now I've got the limit from the left and from the right being 3. And also f of 1 is 3, satisfying all of our conditions for continuity, right? I'll do another one like that. So that one was C. D. Let's say that I had g of x being equal to 4 sine x over x for x being less than 0, and a minus 2x for x being greater than or equal to 0, right? So in here, again, we're going to look for all those conditions. And notice that we're doing things around 0. So we have to make sure that that's what we're approaching, 0, from the left and from the right. So the first thing I'm going to look at is, well, what is g of 0? Well, we can't figure that out yet because I gotta plug it in down here, right? But essentially, g of 0, well, if I plug in 0 into x, well, a minus 0 is just a. Well, that doesn't tell us anything. We gotta do more stuff. So now let's look at some limits. If I take the limit from the left, so I'm gonna do the limit as x approaches 0 from the left of our function. Now, from the left, we're up there, right? We're in the first definition of this. So we end up with the limit as x approaches 0 from the left of 4 sine x over x. You may or may not recall this, but the limit as x went to 0 of sine of x, so maybe I'll write that over here. Recall the limit as x goes to 0 of sine of x over x equals 1. All right, so in there, that's just overall that limit, so it doesn't matter if it's one-sided, this is still going to just go to 1. So this is going to be equal to just 4. So that's the limit that we want to approach, and that's the actual value that we want. So that's going to tell us now that we need g of 0 to be equal to 4. So that tells us that a is going to be equal to 4. But let's do the other side first, the other limit. So we have the limit as x approaches 0 from the right of our function. Well, that's going to be the limit as x approaches 0 from the right of a minus 2x. And that again is just a, right? Because if I plug in 0, 2 times 0 is 0, 9 minus, excuse me, a minus 0 is just a. And we want these two to be equal to each other. We want that the limit from the left, so limit from the left to be equal to the limit from the right of our function. That's just f of x. All right, cool. So we want those two to be equal to each other, so a must be equal to 4. Done. All right. And I'll do one more, and then I'll call it the end of the video. So that was DE, right? E. Yeah. So in here, let's say that I had f of x being equal to a e to the x minus 1 plus 3 for values of x being less than 0. And we're going to say that it is arctan of x minus 1 for values of x being greater than or equal to 1. Sorry, greater than or equal to 1. So again, we need to figure out limits from both sides. So let's do the limit from the left. So the limit, and that's this limit, the limit from the left of 1, we're in this scenario up here, right? That's the left of 1 of our function. Well, that's going to be the limit as x approaches 1 from the left of ae to the x minus 1 plus 3. Plugging in 1, 1 minus 1 is 0, so I have e to the 0, which is just 1, so I end up with a plus 3. Let's figure out the limit from the right of our function. Well, from the right of our function, now we're in this scenario down here, right? So at that point, we're going to say we have the limit as x approaches 1 from the right of arctan of x minus 1. Plugging in 1, I end up with arctan of 0, which is 0. So again, we want these two to be the same. So what we're going to do now is we're going to say let a plus 3 be equal to 0 so that a is negative 3. All right. So that's how we solve those kinds of problems. All right. Now I'll end the video now.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.